Hi, everyone, and welcome to our presentations today. We have a bunch of students who are here to share some of their really awesome scientific presentations with all of you. Over the past 8 weeks now, we've had 36 different students creating 36 different scientific research projects about all sorts of things. And we're going to showcase a few of them here today. As well as tomorrow on Thursday, and then next week in Wednesday and Thursday. We don't quite have time to share the presentations, all the presentations of all the students, but we will be putting out a publication highlighting all the awesome scientific research that we have today. And so our first presenter here, we have Ryan Lee, who's going to be sharing his work. How are you doing today, Ryan?
I'm doing pretty good.
Great. Well, thanks for sharing. I'm going to add Ryan's presentation right here. I'm going to duck out of the stream and let Ryan take it away. He'll share his presentation. We'll have time for maybe 1 or 2 questions about Ryan, and then we'll move into the next student after Ryan, which we have Colin in there. So Ryan, take it away.
All right. Thank you, Spencer, for that great introduction. So my name is Ryan Lee. I'm a rising junior at Monte Vista High School. And I just first like to take this opportunity to thank my mentor, Miss Zhang from the National Severe Storms Lab in Oklahoma. For without her, this project would not have been possible. So without further ado, let's get into it. So an introduction for my project is that as human greenhouse gases emissions increase, global average temperatures also increase. And what we've seen is that over the last 150 years, the global average annual temperature has risen around 0.85 degrees Celsius. And as this global temperature increases, there is a higher probability of dry conditions and hot temperatures occurring at the exact same time. And thus, in my research, the severe California drought of 2012 to 2016 was examined. Now, I basically looked at 2 variables besides the temperature, which is ENSO, which is the El Nino Southern Oscillation. And this is measured using a scale known as the MEI, where positive values indicate hotter conditions and negative values indicate colder conditions. And I also looked at the PDSI, which stands for the Palmer Drought Severity Index. So positive values on the scale indicate wetter conditions, and negative values indicate drier conditions. And basically the scale measures the dryness of an area. So my research question was, during the period of drought California experienced from 2012 to 2016, what caused the sudden jump in temperature in 2014? So my independent variables were carbon dioxide, ENSO, and PDSI. And my dependent variable was temperature. So my hypothesis was that I think that all of these factors play a role in the occurrence of drought, but CO2 had the largest impact on the temperature spike in 2014. So for my method section, I basically first obtained monthly average high-low temperatures for these 3 cities from a NOAA data set, and they range from 1971 to 2016. Then I analyzed this temperature data, and I found the annual temperature anomalies for each of these 3 stations using a baseline of 1971 to 2016. Now, I plotted this with the closest CO2 monitoring station located in Trinidad Head, and also calculated the CO2 anomaly using a baseline from 2004 to 2016. And then I compared these average annual temperature anomalies to the respective locations' historic annual mean PDSI, which remember is the dryness of an area, as well as to the MEI from the Pacific Ocean. And basically I noted any trends or correlations in these graphs. So basically what I used was a t-test calculator as well as the data set locations. All right, so in figure 1, you can see that over the past 50 years, there has been a trend of increasing temperatures in all 3 locations. So you're looking at Los Gatos, San Francisco, and Oakland average annual temperature anomaly. And you could see that 2014 showed a particularly prominent spike in temperature anomaly. So basically, I ran a t-test on this temperature anomaly, and it showed that all of the temperature anomalies for all three stations were significant because they were below the 0.05 threshold. And for figure 2, you could see the individual bar graphs for each of the three locations. And the overall Bay Area average increase, temperature increase, was calculated from averaging the all three data graphs using the endpoints from each graph. So I just subtracted the highest endpoints of the trend line from the low endpoint of the trend line. All right, now in figure 3, you could see CO2 anomaly plotted with annual temperature anomaly. So you can see that there is a really steady rise in carbon dioxide, and the R squared value, which measures the strength of the correlation, is greater than 0.99. So it's really steady in that sense. But there was a lower R squared value for the temperature data, and the R squared value for that was 0.157. And in figure 4, you could see all of the three variables, temperature, PDSI, and MEI, plotted together on the same graph. And the trend lines you could see are basically the 3-year moving averages of each of these respective series. So basically what we discovered was that there was an overall 1.4 degree Fahrenheit or 0.78 degrees Celsius average warming in the Bay Area. And for each city, on a city scale, this ranged from 0.8 degrees Fahrenheit to 2.6 degrees Fahrenheit. Now, this is mostly due to CO2 and the greenhouse effect. As there's more CO2 present in the atmosphere, the greenhouse effect becomes enhanced, and thus the temperatures would go up. But the 2014 significant temperature spike for all three cities ranged from 2.6 to 4 degrees Fahrenheit. And this is likely due to factors other than CO2, because there was a steady rise of carbon dioxide during this time period. So between temperature and MEI, which remember measures the El Nino Southern Oscillation, had a close correlation with the 3-year moving average, with the former trailing the latter until 1997 to 1999. And after that time period, the correlation flipped. And we also examined temperature and PDSI, which measures the dryness of the area. And using a 3-year moving average, we found that it had some inverse correlation. And this correlation was most pronounced after the year 1998. But in 2014, we discovered that MEI was not actually historically significant. And remember, 2014 is the year with that huge temperature spike. And this is due to the fact that in 1981 to 1983 and 1990 to 1993, there were similar or greater MEI values without a similar temperature spike seen in 2014. And in 1990 to 1993, the other variable, PDSI, was between -1 and 0. Thus, it had little effect on the MEI itself. Now, there was extreme dry periods before in the years 1985, 1989, and 1987, And these values were respectively -2.19, -2.03, and -2.09. But during these 3 years, there were also mild to cold La Nina episodes. And these MEI values were from -0.39 to -0.52. Thus, this could indicate that the PDSI had limited effects on temperature increases due to the MEI countering the PDSI, or that the MEI was insignificant and that PDSI itself didn't have that much of an impact on temperatures in the Bay Area. So these two cases show that the combined effects of MEI and PDSI, either a high MEI and a low PDSI, or a low MEI and a high PDSI, have the greatest impact on the temperature in the Bay Area. But when they are out of sync, then the impact on the temperature is limited. So we found that overall there's a high El Nino, but combined with a very low PDSI, this resulted in the temperature spike, which occurred in 2014. So there are also some limitations in this study, which is that the CO2 data came from Trinidad Head, which was around 250 miles from the Bay Area. And this could bring up problems because there may be potential variation in CO2 trends in different locations. But overall, we found that higher temperatures and larger negative PDSI values could lead to extreme temperature increases, and these may get more frequent in the future. For the area we studied was just until 2016. Now, it also demonstrates that these two variables have a significant impact on temperature through quantitative analysis. And it also proved my hypothesis incorrect. For both PDSI and ENSO were found to have a greater impact on annual temperatures than carbon dioxide did. And these warmer conditions, due to high MEI, could lead to drier terrain, which basically means there will be a lower PDSI value. And this leads to less water, just in general. And thus, more solar radiation from the sun will be converted into sensible heat, which is basically radiation which you could feel, rather than latent heat, in which the sunlight would be converted or be used for converting liquid water into water vapor. And this basically takes away the heat from sensible heat. So there would be more sensible heat than latent heat with less water available. So further research, if I had more time to conduct more research, this research currently links global warming to droughts and jumps in temperature, or at least the frequency of these. And we would need to further study spatial variations of CO2 and CO2 fluctuations as well. And we would like to incorporate more temperature data from other Bay Area cities, as this would be more representative of the entire Bay Area rather than just the 3 locations we selected. And we would like to increase our time span of study so it could potentially eliminate any biases which are currently present in our current data set. And it would be interesting to investigate the impact on biodiversity in both the Bay Area and California. And particularly, we would like to study desert ecosystems, which are already scarce on water. So we like to see what warmer temperatures and less water availability would actually affect the desert ecosystems, how it would actually affect it. All right, that's my work cited for the presentation. Thank you so much.
Awesome job, Ryan. This is a really great presentation. And up next, we have Colin. But before, Ryan, you go, I just wanted to give anyone at home who's watching along any chance to ask Ryan a question about his research. You can do so in the comment section, and we can try and do that. But just to kick us off, Ryan, I do have one quick question for you, and kind of what caused you to be interested in temperature and CO2, and what about this caused you to choose this for your research project?
Well, I mean, we've heard a lot about like frequent droughts, and I've particularly heard about the news about like the 2012 to 2016 drought period in California. So I was wondering if those same variables could be seen, and their trends can be seen on a more local level. So if we could use local conditions as an indicator as to whether the conditions, like whether there's like low PDSI or high MEI, and this like potentially affect the temperature record in these local cities rather than of the entire California state.
Perfect.
So it really got me interested.
That's great. And then last question is, what was the hardest part, or one of the parts you had to work the hardest in on this project?
I think honestly, it would be the data collection, because all of these data sets, they often have different amount of coverages, or they had different time spans. So it's really working to consolidate all of those into similar time spans so that the data present would be the most accurate for all of the data sets. So we have the most accurate results.
Perfect. Awesome. Well, thank you so much, Ryan. I really appreciate you sharing this awesome presentation. And so up next, we are going to have Colin share his presentation. And Ryan, if you can get the chance to stick around, we'll have a little bit of a thank you at the very end. I've got Colin here. How's it going, Colin? I think you'll have to unmute yourself.
Doing well. How are you?
Great. And then I'm going to add your presentation in there. And if at any point any of you watching at home have a question for Colin about his project, feel free to leave that in the comments and we can answer those at the end of his presentation. All right, Colin, there you go. You're all set, and I'll let you take it away.
All right, perfect. Yeah, so thanks for the introduction, Spencer. Like you said, my name is Colin. I'm a rising junior at the Nueva School located in the Bay Area. And for this summer project, I looked into the relationship between slope, the slope of a terrain, and vegetation present. My mentor was Julia Kelson. She was a big supporter in this project, very knowledgeable, very helpful. So big shout out to her at the beginning. And so, yeah, let's get right into it. Brief introduction on what I did. So like I said, I analyzed the correlation or the relationship between slope of a terrain and its vegetation that's present. And a little bit of past research, doing research suggests that vegetation is controlled by different patterns in terrain, a combination of elevation, the material, the slope, the aspect, which is the direction of the slope relative to the sun, and then climate. And so looking into some past research, Larson and others, they examined the presence of woody taxa on cliffs. And what was surprising to me after reading the article was that actually cliff terrain supported vegetation. And here's a quote from here that says, "While we do not claim that the cliffs examined were randomly sampled, all were vegetated to some degree, and most of them supported woody taxa." It's kind of not bizarre, but a little shocking, surprising that, you know, a higher sloped terrain could support vegetation. So that kind of prompted my interest in analyzing the slope, the correlation or relationship between slope encompassing all ranges, not just cliff like terrain, and vegetation. So that's a brief introduction. My specific research question with regards to this project, I set it out as, how does the slope of a terrain affect the presence of vegetation? And then one thing I wanted to do, which unfortunately I didn't have time to get to, was like looking at how we can use this information to predict the amount of vegetation elsewhere, given the slope, based on like the samples and data analysis that I did, because I chose a specific location to investigate this. So my independent variable is the slope of the terrain. That should influence my dependent variable, which is vegetation. I measured vegetation using a variable or a statistic called NDVI, which measures the density of green within a certain patch of land. Returns a number between -1 and 1. -1's like water, 1 is very green. More on my research question, defining a specific hypothesis. My hypothesis is that the lower slope terrain will be more supportive or produce more vegetation, and that the correlation will be between the two will be negative, meaning that, you know, as slope degree increases, vegetation will decrease. Even though Larson examined, you know, that higher sloped areas or cliff-like areas can support vegetation, this is just my hypothesis. My rationale and reasoning for this is that higher slope terrain is more susceptible to erosion or more intense rock and soil movement, whereas lower terrain, you could say, is more structured or stable, less active, kind of leading to a less active and more quiet environment that provides what I think support for vegetation growth. So this is my hypothesis. And going into materials and methods on kind of how I analyze and examine this relationship, what I did was I downloaded 2 LiDAR, standing for light detection and ranging, data sets for both slope and then NDVI, Will National Park. I love going there for road trips and stuff, being kind of close from the Bay Area. So I chose to look into that as my sample place. What I did was I used QGIS, an open source geospatial analysis program. And what I did was I processed and polished these 2 satellite data sets. And what I did was that I projected them into the same resolution in the UTM coordinate system, which meant that for every point where there is slope, for every slope point, there is an NDVI point. So therefore, I can examine the correlation between the two. And specifically how I examined this was I drew 4 transects, which were just lines across the mountain and valley, which generated 2 columns of data, an X and a Y, one for slope and one for NDVI. Basically, these transects I chose, they spanned across the valley, which was low slope, and cliffs or kind of mountain hillsides, which are higher slopes, basically encompassing all different degrees, so that I could analyze the relationship and that I didn't have one or just the other. Another thing going into controls or how I eliminated other influencing factors, because vegetation is controlled by, a lot of stuff. It's not just slope. Basically, Yosemite Valley is relatively small, so there won't be extreme variation in the climate. It's not, or the weather. It's not like it's going to rain a ton on one side of the valley and not on the other side. And in addition, the soil type is relatively the same. It's a big granite kind of location. Granite's all that's really there. So the soil type on one end of the valley versus the other is not going to be significantly different. And lastly, a benefit of choosing Yosemite Valley is that the landscape itself, like I touched upon on the other slide, contains a wide variety of slopes, from low sloped valleys to high sloped big granite cliffs. So that allows me to analyze the relationship between slope, all slopes and all degrees. Hypotheses for statistical tests. So I use inferential statistics to kind of analyze this. I need to set out a null and alternative hypothesis. My null, which you can think of as like the boring one, is the mean NDVI of 75 to 90 degrees is equal to the mean of 30 to 45 degrees. Before I go a little further, I wanted to talk about why I chose 75 to 90 degrees. I might touch upon that later in a later slide, but I thought I'd bring it up now. The data of slope range from 0 to 90 degrees, and I grouped them into buckets of 15. And I chose 75 to 90 as the quote high sloped areas and looked at the NDVI and vegetation present there. And I chose 30 to 45 degrees as the lower ones. This is why I want to touch upon it. I chose to exclude 0 to 30 degrees because after analyzing this and looking at NDVI levels and also comparing it with Google Earth, you could see that there were a lot of roads, cobblestone paths, rivers, dead grass patches areas, hotels, and that can throw off the accuracy of NDVI to a certain extent. So I just compared 30 to 45 degrees as a low one. Oh, and in addition, there's a lot of erosion rockfall, and they kind of pile up. And of course, that's not gonna it's gonna prohibit the presence of vegetation. So briefly, that's why I chose 30 to 45 degrees as my low sloped area of analysis and 75 to 90 for my high and slope. So yeah, moving on, my alternative hypothesis is that the mean of NDVI of 75 to 90 degrees is less than the mean of NDVI of 30 to 45 degrees. This is kind of my hypothesis. Higher sloped areas is less supportive to vegetation growth than lower sloped areas. And my alpha value, which you need to define, was 0.05, and that's also directly proportional to my confidence intervals, which I'll talk about later, of 95%. So those two things are like proportional to each other. Another thing to note is that I did a one-tailed test. This is because my assumption or my hypothesis is that 75 to 90 degrees sloped areas is less supportive to NDVI than 30 to 45, and not that it's just not equal. So if it was just not equal and it could go either way, more or less, then it would be a two-tailed test. But since I'm saying that I believe that 75 to 90 degree range will not have as much vegetation present than 30 to 45 degrees, that's why it's a one-tailed test. And what I did was I conducted 2 types of statistical tests. I did confidence intervals for a mean with an unknown population standard deviation, which meant I had to use a t-score, and hypothesis tests for the difference between means. These ultimately helped analyze the relationship between these 2 buckets of slopes, which I analyzed. Here's some of my data. On the left, I don't know if you can see my arrows. Hopefully you can, or my cursor, but if not, it's no problem. On the left, we have the transect plus the range. So for each transect 1 through 4, we have a pair of different ranges, 75 to 90 and 30 to 45. We have the mean NDVI, which I calculated just using average. And what I did based on that and the standard deviation and a T-score for 95 confidence level was I created confidence intervals. Basically, you estimate the range that the mean will lie in with an unknown population. So based off the sample I drew, I could estimate with 95% confidence that for specifically 75 to 90 degree range of transect 1, the mean NDVI lied between 0.18 and 0.25. So yeah, I did that for all of the transects in each of their ranges. And in addition to that, like I talked about, I did a hypothesis test, which returned a p-value, which determined whether my results between the two ranges were statistically significant or not. And as you can see on the right column, the far right column under p-value relative to my alpha of 0.05, it's very statistically significant, or it is statistically significant between the two. Talk a little bit more about what that means in the discussion later. Data figures. This one kind of helps visualize my confidence intervals. On the x-axis, we have the transect number, so T1's transect 1, and then which within each of those transects, we have 75 to 90 degree data and 30 to 45 degree data. We have 4 pairs of confidence intervals. Blue is lower bound, red is upper bound. Demonstrates that there is statistical significance between the two slopes for all the samples. Forgot to mention another way to test for statistical significance is to look whether the two confidence intervals overlap. And you can see for all the pairs, like for example, transect 2, we have 75 to 90 and 30 to 45. These ranges do not overlap, and you can conclude that there is statistical significance. So this is just a good visualization to show that for all of these 4 transects that I sampled, there was statistical significance between the two, which supports my hypothesis that lower sloped, areas are more supportive than higher sloped areas. Another thing is histograms displaying the distribution of NDVI or vegetation present for the 2 separate ranges of slope. On the left, we have 30 to 45, and you can see that it's left skewed with a kind of a median or an average of up towards 0.61. So it's a lot more vegetated than the 75 to 90 degree range, which is right skewed, meaning that there's less values out towards 1, an NDVI level of 1, meaning that it's very vegetated or highly vegetated. And you can see that it's centered around 0.14, which is very low relative to the histogram on the left. This is another supporting visualization or graph. So going into the discussion, all 4 transects, as I said, all these samples, they return statistically significant data between 2 areas of slope that I observed. Basically, this is supportive of my hypothesis that slope influences or has an impact on NDVI vegetation. In addition, like I mentioned in the last slide, the histograms, they show a shift in distribution of NDVI, or I guess vegetation, in the 2 ranges of terrain slopes. And I forgot to mention, or another thing to mention is that the R-squared for the 4 transects was really low. Basically, that means that slope isn't the only factor that influences vegetation. However, because of this test that I did, just comparing vegetation and slope, I conclude that there is statistical significance between these 2 categories. And yeah, touching on a bit of sources of error, R-squared suggests that there were perhaps other controls that were not accounted for. Maybe there's moisture levels, differences in the transects that I measured, or some other factors can influence NDVI that's present, not just slope. And also that perhaps the 4 transects that I drew didn't have 100% accurate data, or the conclusions were made with too little data. In statistics, more data, the better. So getting into further research, one thing I didn't get to, but I wanted to look into, was looking at a 2-way regression for predicting vegetation. So in addition to slope, maybe soil, maybe moisture, aspect, etc. Because as R-squared showed, with a low R-squared value, there's obviously other stuff that influences vegetation, not just slope. As I said, survey more data and transects to have a bigger sample size. Stats, you want more sample, you want more data. All it does is increase accuracy and precision. That's always better. And in addition, what I want to do was apply it to other landscapes, which I didn't have time to get to, that's similar to Yosemite, glaciated landscapes, such as the Rockies, the Sierras, and more, all that kind of have that granite thing and have sprung from the movement of glaciers. And lastly, look for a difference between different terrains and the results. So maybe looking into a desert terrain or a landscape versus Yosemite, which is a granite and mountain terrain, and kind of seeing how different landscapes and the soil that's present there can affect vegetation as a whole. That being said, that concludes my presentation. I had a blast with Headwaters this summer. It's been a great 8-week journey working with Spencer and Julia and the crew here. So yeah, big thank you to those guys. And yeah, any questions?
Awesome. Thanks, Colin. Let's pop right into this question here from Laura. If like one of the reasons there might be less vegetation on those slopes, and like why that would be. Do you have any thoughts on Laura's question and the answer for that based on your research doing this?
Sure. Yeah, I didn't examine kind of looking into how plants were able to structure the roots, but going into my initial hypothesis and what I thought about was there would be a lot more movement with the rocks. They'll be more susceptible to erosion. Probably higher slopes are higher up, maybe more weather, more rain, just a lot more action in general. So I think that could have been one of the reasons, and especially that roots kind of go more into the soil. They might have trouble if the rocks are constantly moving, if soil levels are constantly shifting. So that would be my guess. I didn't look exactly into that, but yeah, that would be my guess. So hopefully that answers your question.
Awesome, thanks. The next question that we have for you is this direction that the slope is facing might have an amount on the vegetation. Yes. What do you think that might be if you had to take a guess, and how might you be able to answer that question?
Big yes. Yeah, I remember looking into this. I couldn't find data for aspect, which kind of is the way that slope faces. The slope of a mountain range or a terrain faces the sun or is relative to the sun. But that definitely influences vegetation. I don't want to say because I'm guessing at the moment, but definitely north versus south, they have a big impact. And if there's pictures that I've seen where some side of the hill is very vegetated and then the other side just has, bushes that, can't get as much moisture or sun exposure. So definitely yes. That's another thing that I wanted to touch upon or kind of mention in further steps would be looking at aspect plus slope, because those aspect definitely influences vegetation. So that would be a further steps. And to answer your question, yes.
Cool. Awesome. And then one last question before we're going to move on to our next presentation with Arnab.
Yep.
And so just same question asked Ryan, why were you interested in slope and vegetation, and what caused you to come up with a research question that you did?
That's like a really good question, actually. Like I said, Yosemite, I've been there a lot. It's a beautiful place. I love nature and the outdoors. So yeah, that's kind of why I chose Yosemite Valley to examine vegetation. But specifically, I wanted to do just an inferential statistics project. Less concerned with the variables that I examined and more about predicting, kind of evaluating the mean from an unknown population was more of interest to me. But I think I picked vegetation. Yeah, it's actually a really good question. I don't actually have a direct answer to that, but more about inferential statistics for sure.
Cool. Awesome. Well, thank you so much, Colin.
No, thanks for having me.
Appreciate you sharing this. And up next, we are going to have Arnab in his presentation. I'll add him to this stream in just a moment. There we are. Hi, Arnab. How are you?
Hey, Spencer. Thank you for having me. I'm good.
Great. And so your presentation is up here. I'll leave you to it. And if anyone has any questions as we go, feel free to put them in the comments section, and we'll take a look and talk those over at the end.
Cool. Thank you, Spencer. Hey, everyone. So my presentation today is, my topic was the correlation between the shutdown orders and the CO levels across the United States. First up, I'd like to thank Daniel for helping me. He was my mentor, and I'd like to thank him for helping me throughout the project. He helped me with the R code and stuff, so a big shout out to him. Okay, so my question that I asked was, it was important my question was, how has the quarantine during during the COVID-19 pandemic affected the levels of CO in states that were hard hit by the virus? I asked this question because since the pandemic first emerged in December 2019, it's about 7 or 8 months from now, almost every single country has gone into either a local or a nationwide lockdown as an effort to prevent the virus from spreading and hurting both the citizens and the economy. So the virus has actually affected us in more than one way. That's like health and stuff. That's obviously it's hurting our economy and our health, but it's more than that. It's also important. The question is also important as it tells us it's more than data. Since I don't know if you guys have heard, but a lot of the major companies like Google, Facebook, and Twitter, they have announced that their employees can start working remotely because during the pandemic they've actually realized that they don't really need buildings, and people can actually and Google's actually paying their workers to stay home. So that's a plus that we've realized, and I think this question makes a bigger it gives birth to a bigger question which is asking if offices and buildings are really necessary. So yeah, that's why I picked it. In conclusion, the data from the EPA shows that the CO levels have fallen from January, with some states seeing dips in the lockdown when the lockdown first came into effect. My question, like I said, was how has the lockdown during COVID-19 affected the levels of CO? My independent variable in this case was the JACE since January 2019. So I started analyzing my data from January 1st to for some states until July and for some states until as early as March. And I'll talk about that a bit later. My dependent variable here was the levels of CO. My hypothesis was because of the lack of human activity and public places shutting down, offices and schools transitioning to remote learning, and factories shutting down, the CO levels would decrease as people aren't commuting and buildings aren't being used. I primarily chose this hypothesis because, for example, I live in the Bay Area, and the Tesla factory was a big contributor to the pollution levels, and that shut down when the pandemic first emerged. So I think it's interesting seeing how being in the Bay Area, the factory shut down and how that would affect the levels. So that's why I'm sticking to this hypothesis. My materials and methods. So the data I used was obtained from the EPA's public pollutant levels. The EPA has a page where anyone can just log onto their website and access the levels of CO, SO2, PM2.5, PM10, NO2, and the various other pollutants. So I downloaded the C and PA data sets as a test to just make sure my project was actually it actually made sense. I then imported them into RStudio. RStudio is a tool that's used by scientists and researchers to figure out to perform data analysis. So yeah, I imported them into RStudio. So RStudio has packages that you can use. Some of the additional packages I used was dplyr, ggplot2, plotrix, and ggprobar. So when I imported my data onto R, I cut down the important and viable data. For example, I just cut down the data with the date, the levels, and the site name. So the mean from 6 of the states that were hardest hit, in my opinion, that was California, Pennsylvania, New York, Texas, Florida, and Arizona. They were taken. So the means from each of those states were taken for each state across every single county or like every county that was available, and various sites in each county. So there was a healthy variation, and there was a lot of data. So to be clear, there was data in each site. So there were many sites in each county, and there were many counties in each state. A core test in the R-square value was used to verify the results of my data. Okay, so this is one of my first figures, and as you can see on this graph, this contains the Arizona, California, and Pennsylvania graphs. So the shutdown dates in Arizona was March 31st, California March 19th, and Pennsylvania April 1st. So right here, as you can see in Arizona, the shutdown began right about here, or actually, yeah, right around 90 days. So right about here. And you can see that after the shutdown began, or even rather before, the people actually started to stay home, and they didn't go out as much, which led to the data being very close to the linear model right here. As you can see, for example, in Jane, it's varying and it's really high. It goes low and high. Then closer on this part, it's definitely for the most part it's lower than the linear model. And as for when the Arizona started reopening, so for Arizona, actually, I had data until July because the EPA provided the data until July. So Arizona started reopening in about this phase right here. So as you can see in this part, the variation was really low, and it was definitely under the linear model. But as the states started reopening, the CO levels spiked back up and they started fluctuating again right here. So that just goes further to prove my point. The same thing for California. I unfortunately had only data until March, and until March 30th, so that's a bummer. But I did what I could. Even in California, there was the CO levels were definitely closer to the linear model, and compared to January and February. For Pennsylvania, also there was actually a really big dip as the lockdown first emerged. That was around right here, and as you can see, it goes straight down on here, and then it's a lot closer to the linear model again. Here are some of the other states. For Florida, Florida is also pretty much the same thing. Florida's kind of lesser variation, but still present. And again, it's definitely closer to the linear model. I included New York because, well, it was the state that was hardest hit about the virus first, and it was actually the state with the most cases up until a couple of weeks ago. And even here, the variation was really high, as much as one value being as much as 1 ppm in one day. But then after lockdown emerged, the highest value was around 0.4 on one day. So I think that's like more than double. So that shows, again, just proving the point. The same thing for Texas. The variation was really a lot bigger, I think, in Texas for the most part. And as the lockdown emerged, it definitely went down to the linear model too. So I wanted to talk about Arizona again. This is a much clearer graph because that was mostly vertical. Here you can see the lockdown was around this period from like 50 to 100 date, and as the country reopened, the variation started rising back again. The values didn't start rising back again, but the variation started emerging, and I'm pretty sure the values are at least halfway or more than halfway now. So overall, I think my hypothesis said that the CO level will decrease, and the data shows the same for pretty much every single state, if all of them. So the data looks like it did primarily because the population started staying at home before the lockdown even emerged and restricting non-essential tasks like going to the movies or going to the park, stuff like that. In addition to that, the buildings, factories, offices also closed, which put a less strain, which led to the buildings not being used at all. And when buildings are not being used, well, there's no air conditioning or there's no heating, which means there's less energy, which means there's less pollution overall. And this research has been definitely backed up by other projects done from other reputable scientists. There was a study in China after the virus first emerged in Wuhan, where the pollution levels of every single gas, not just CO, was significantly lowered, and that was in all of northern China where the virus first emerged. So I think that's my data is backed up with those types of studies. And since the first case in the United States first emerged on January 20th, people have been trying to stay home, like I said, and restrict any non-essential work. That's why I think my data looks the way it did. So the future research could definitely include more experiments regarding how pollution level spikes as we reopen. We saw a brief spike in Arizona, and this could, I'm pretty sure we could do more studies on every single state like this with more data. There could be experiments on how to solve climate change problems, seeing how the lockdown for 3 or 4 months affected the CO levels, almost cutting it in half or even in some cases lower. That could bring up some really interesting questions. And there could also be studies discussing if being in a lockdown is worth hurting the economy and healing the environment, because there's more studies. There's one in China, like I said, and there's another study in the worst polluted city in India, in the world, that's Delhi. That has also, the pollution levels of there have also been coming down. So I think this just gives rise to a lot more questions, and it's just the beginning. And these are some of them we're excited. And that's it. Thank you for having me.
Awesome. Thank you so much. I have one quick question to get us going, and then if anyone else has questions, feel free to put them in the comment section. Arnab, I don't know if you can skip back to any one of the time graphs,
Sure, yeah.
figures, but one thing that I kind of, that's any of those are great. It seems like there might be, it looks like to me, my untrained eye, that during the shutdown orders, there's less like daily variation day to day or within a day. And then as things reopen, or kind of earlier before that, there's more variation in the CO2. And I was just wondering if you had any thoughts as to why that might be, or is that really a pattern that we're seeing? Let's see. I think you're muted there. If you can unmute yourself on the bottom.
Can you hear me now?
Yep, that's great.
My earbuds just died.
Ooh, let's see. We can't quite hear you there. We were hearing you when you had your earbuds in.
Could you say something, Spencer?
Yeah, I can hear you, and that's great if you want to go ahead.
Okay, I can hear. I'm sorry, my earbuds connected back again. Could you please repeat the question?
So it seems like that during the shutdown orders, the day-to-day variation in CO levels is less than kind of earlier or maybe after things have shown up. Like there's some spikes, but there's some valleys, and then like the change between one day and another might be more variable outside of the shutdown period. And I was wondering if that was a pattern that you looked at, or if you had any ideas as to why that might be.
Yeah, I can talk about that with the Arizona data because that was the only data that I had until when the states reopened.
Yeah.
I think that's primarily because Arizona, well, like I said, the governor really wanted to open up the state, so that allowed like restaurants, factories, and some offices to open up, which just allowed more buildings to work, and then more factories to operate, and then more businesses to actually have their business sorted, which just led to more commute and then more pollution, which is why I think the sea level increased back up.
Cool. That's great. And then the last question we have for you before we move on to Annie's presentation is if you had any or looked at any other sources of human CO that didn't change during the shutdown. What sources might there still be?
There's definitely still some businesses, because there's some businesses that just can't shut down. Like there's some public shops that need to stay open for people to get food and stuff.
Mm-hmm.
Definitely like groceries and the shops mostly. I guess you can include like government offices there, but most of the states I looked at didn't really have many offices that were open. So I'd mostly say just shops and essential businesses. Like hospitals have to stay open, obviously, stuff like that. Yeah, I think that's it.
Mm-hmm. Awesome. Well, thanks, Arnab. That's awesome. I really appreciate all of that. And if you could just stick around, we'll do a short thank you with all four of you at the very end. But with that, we're going to move over into Annie's presentation. So thank you so much.
Yeah, thank you for having me.
All right. Hi, Annie. How's it going?
Pretty good.
Great. I'm going to add your presentation to the stream here, and we'll let you go to it. And then at the very end, we'll do a couple questions just like that. And then we'll give everyone the chance to come on and say a quick thank you before we wrap things up today.
Yeah, so hi, my name's Annie. I'm currently a rising junior at Los Altos High School, and Spencer was actually my mentor, so huge thank you to him for helping me with my research project and everything. So my research topic is focused on how someone's age and knowledge can affect their views on climate change and their actions regarding it. So while doing some background research, I'll just start with some issues that like climate change can cause. So there are a lot of negative effects that climate change can cause. So it can cause more droughts and heat waves, which can lead to more prevalent wildfires like you can see in California, and fewer water supplies in other areas. It can also lead to more hurricanes, because hurricanes are fueled by warm water. So as sea levels rise, then hurricanes can become stronger and more prevalent. Climate change can also lead to rising oceans, which can lead to coastal flooding. So this shows that climate change doesn't only affect the environment, but also people and other communities. So while doing background research for my research project, I found that younger generations are more likely than older generations to believe that climate change is an anthropogenic issue, which is just basically an issue that's caused by humans, but they're just as likely as any other age group to take action to reduce their impact on the environment. I also found that increased knowledge about climate change is correlated with acceptance of anthropogenic global warming. So these studies helped me figure out my hypothesis. So my research question was, how does age and knowledge of climate change influence people's actions regarding climate change? So my independent variables were age and knowledge, and my dependent variable was someone's actions regarding it. So my initial hypothesis was that younger generations would be more motivated than older generations to combat climate change, but would actually take less action because of their lack of resources or some other factors that might influence it. I also hypothesized that people who had more background knowledge on climate change would try to lower their impact on the environment more than people with less knowledge. So basically, I created this survey that asked questions about the person, like their age, their gender, and all of that stuff, along with climate change questions. And I actually teamed up with another student who also had like a similar topic, and then we both combined our two surveys, and then we sent it out via the Headwaters newsletter and to like friends and family that we knew, and asked them to share it as well. We also shared it via a paid Facebook promotion, which Spencer helped us figure out, along with Leah, who also really helped us share this survey with other people. And those were the main ways in how we shared our survey. So a lot of my questions regarding climate change asked about the frequency of how often like someone did a certain action. So then I developed this point system to make the survey questions that asked about if someone did something daily, weekly, or monthly, to make those questions more quantifiable. So each response was basically given a certain number from 0 to 6, with if you never did something, it was 0. If you did something yearly, it was 1, and so on. And then depending on which action was being asked about, a portion of those points would be given to that person that was proportionate to the carbon output or the carbon saved by doing that action. So like, for example, let's say someone answered that they flew a plane once a year, so then they would get -1 point for that. Or if they composted daily, they would get 0.024% of 6 points that they would have earned. So yeah. So what I found from my data, which I put into SPSS to help me do my statistical analyses, I found that people between the ages of 21 and 30 tended to believe that climate change is a large issue. And while like a lot of other age groups also believed that climate change was a large issue, they had the highest score, I guess. I also found that when I compared the background knowledge with how large of an issue climate change is, I found that the overall trend was that a higher level of background knowledge was positively correlated with the belief that climate change is a large issue, which can be seen through the graph. And my p-value for that was 0, meaning that it was statistically significant, but my R-square was fairly low, so there was probably other factors that also contributed to the scores. I also found that when comparing age with the total points earned, and that older people tended to earn more points, but there's still a large amount of variation within each age group, so it's still sort of unclear. Yes, and then the total points earned are just the point system that I mentioned earlier that I created to see how much action someone would take in a year. And when I compared background knowledge with the total points earned, I found that, again, a higher level of background knowledge meant a higher number of points earned. And my p-values for both of these were lower than 0.05, meaning that both of them were significant. So in summary, for my results, there wasn't a really clear correlation between age and their actions regarding climate change because there's so much variation. But then again, that is sort of expected when you're collecting data about people because people are just generally very different from each other. And yeah, the results that I found regarding age didn't really correlate with the background knowledge that I found, because the scientific findings that I found stated that people of different ages were equally likely to take action, but I found that people who were older tended to take more action. I also found that a higher level of knowledge about climate change had a positive correlation with increased action taken to combat climate change, which supports my hypothesis. And some factors that might have influenced my results were that a lot of the people who answered the survey leaned more liberally, because that was one of the questions that we asked. And then that could have been a factor that contributed to the majority of people answering that climate change was a large problem, along with a lot of other questions that we asked. Also, a lot of people were more on the younger side, since not as many people older than 60 answered the survey as people who were like aged 11 through 40. And a lot of respondents were female and from California, so those could have been factors that influenced my results. So basically, the significance of my results are that it helps people understand how important education is in regards to combating climate change. And it could also help environmental policymakers know which groups to target when they're making their policies. They could target people who might live in a certain area, or who don't have as high of a level of education. And my research could also help find out how people are taught about climate change. Maybe they could be taught at like a younger age or something to help combat it in the future. So yeah, future research could include going more into someone's occupation or major to see why people with higher levels of education take more action to limit their carbon footprint. If I had more time, I would also go into more into how ethnicity or culture could impact someone's actions regarding the environment, and possibly how where they live or where like their state or city could impact what they believe about climate change. So yeah, and here's my works cited.
Awesome, thank you, Annie. That's a great presentation, and it's really neat to see all the 4 different presentations that we had today. I'll open it up to any questions that we have in the comments. Feel free to pop those in, and then in just a moment we'll get all 4 of you students to come in, and we just want to say a quick thank you to a couple people who supported this program. The first question I have for you, Annie, is this one from Laura, and I know you and I talked a little bit about this, and I was just wondering if you would try and answer this question in the lens of maybe how you tried to address this issue, or some other things that you could do in future research like this.
Yeah, so when we initially sent out our survey, we saw that a lot of populations weren't represented enough in our survey, because again, as I said, a lot of people were female, a lot of people were liberal. So yeah, I do feel like the data wasn't super representative of everyone in the population, but I guess that's, maybe if we had more time, we could have sent it out to more people, and people in like different religious groups and all that, because yeah, we didn't really have a lot of time for that. But to try to fix this, like I mentioned, we tried to create a Facebook promotion thing where we tried to target certain groups, but we found that didn't really work, so we decided to stop it. But yeah, I definitely do think that our data isn't super representative of the global population.
Perfect. And so the next question that we have from Leah is, what are the larger implications of the general public being concerned or not concerned with climate change? And we'll have that, and then we'll have time for one more question, and then we'll get Ryan, Colin, Arnab, and all of you to join back in there.
Well, yeah, I feel like if with my research, you can see how different groups of people view climate change and how often they take action regarding it. So it would be better to have everyone be worried about climate change, but obviously that's not the case. So I feel like if not everyone was concerned about climate change, then maybe we could, well, if you could target the groups who weren't super concerned about climate change, you could, perhaps slow down global warming or try to find a solution to environmental problems more quickly.
Perfect. And then last question is, what was one of the hardest parts of doing this project?
Probably figuring out how to work SPSS, because before this project, I had no idea how to use it. And I watched like probably several hours of YouTube tutorials trying to figure it out and like what's the best way to, I don't know, label variables, do ordinal regressions and all that stuff. So that was pretty difficult.
Yeah. Well, nice work. That's all some pretty advanced stuff here. And so with that, I'm going to add back in the rest of our students here. And what I just wanted to do is just take a moment and just do a quick thank you. We had a bunch of different organizations and people support to make the summer research program happen. I know myself, including a lot of students, were planning on doing summer science camps or all sorts of things like this. And it took a bit of work to make this happen, but as you all saw, all of these 4 students and all the other 36 students in this program came up with some really neat research. And so I'm just going to share my screen here and let's see, pull up just this thank you for these couple organizations who helped make this whole thing possible. And so I was just hoping that if in a moment we could just do a quick thank you to the Stroptimus Foundation, the Tahoe Truckee Community Foundation, and the Los Altos Community Foundation, as well as a bunch of individual donors who made this program possible to both fund its building and some of the scholarship spots we had for that. And so if we could just do a 1, 2, 3, and a big thank you for supporting this science program, that would be great. All right, you ready? Okay, 1, 2, 3.
Thank you for
supporting the science.
Awesome, perfect. That's great. I hope all of you had a great time watching these presentations at home. We'll have another round of these tomorrow at 5:30, and then next week on Wednesday and Thursday at 5:30. Nice work, Amy, Ryan, and Colin. All of you are awesome scientists and should be really proud of the work that you've done.
Thank you, Spencer.
Mm-hmm.